Good afternoon, everyone. First, I would like to thank Professor Raghavan for giving me this job. And after a good lunch, I'm not in for mathematics, so I'll be preferred to go for stargazing, and I'm sure you will be too. Our guide will be Venkata Balaji from IIT Madras. He got his PhD from CMI, so he's not unknown to us. So I request him, without further ado, to show us the show of stars. Thank you.
So, a very good afternoon to all of you. I thank Sir Raghavan and IMSC and all the agencies who are funding this program for giving me an opportunity to talk here. So, I just wanted to refer to the RSIC program, which is being conducted for the last 3-4 years at IIT Madras, where there's a similar program, but it is for students in high school who have completed 11th standard and going to the 12th standard. And so it's very nice that there is one at the college level, namely this one. So let me give a disclaimer. I'm not at all a number theorist, all right? And the only thing is that I think it's true that no matter what area of mathematics you work in, I mean, number theory, because of its pure simplicity in the statement, in the statements that statements of questions that it asks, that itself attracts people. Okay, and by training, I'm an algebraic geometer, right, and more interested in algebraic geometry and complex geometry and things like that. Number theory is not my forte, but nevertheless, I am trying to learn some number theory, and so whatever account I'm going to give is going to be an account of a person who is learning, not an expert. Okay, so so with that disclaimer, let me continue. So the idea is that, see, in mathematics, of course, we have lots of questions that need to be answered, and it so happens that in number theory, the kind of questions that one asks are so basic that even you can explain the question to even a school student, sometimes even an elementary school student, and the question is very easy to ask. And then trying to prove it is something that might be so difficult that, and that's the reason why number theory is so intriguing. It's amazing in the sense that the kind of questions you can ask are very, very simple questions, and whereas the proofs of these things are proofs of very simple questions, and of course there are still a lot of open conjectures. So the coming back to the title of this talk, so see, the idea is that you think of if you look at the sky and suppose there are a lot of stars, then you should be able to see, if the sky is filled with stars and you look at them, you should be able to see a lot of them, all right? So in this, if you make an analogy of the sky with say real numbers, okay, then the so-called transcendental numbers, if you want to call them as stars, because they are special in the sense that they are not algebraic, okay? So you know when a number is algebraic, and a number is algebraic if it is the zero of a non-trivial polynomial in one variable, okay? And of course we are working with coefficients in the rational numbers, okay? So that's the definition of a number being algebraic over the rational numbers. So a number which is not algebraic is called transcendental, okay? And of course you know, so that's the beginning definition, which of course many of you, so I guess I should not write on this part of the board probably. So let me write down, and I would also urge you to make a note of whatever I am saying. So I begin with the following. So this is a definition. Somehow this is the largest I can write, so I think it may be, I'm used to this size, but anyway, let me write it a little larger. So here is definition. So I guess this is fine. See, so so for our purposes, you can take complex number, okay, or if you want, you can take even a real number for that matter. It's called algebraic over Q if if it is the zero of a non-trivial polynomial in one variable over Q. Okay. So, so this is the definition of what an algebraic number is, and of course the numbers which are what we are interested in are numbers which are not algebraic, and we call them transcendental. Okay. So a number that is not algebraic is called transcendental. And these are the numbers that I would refer to as stars in the sky of real numbers. Okay, and the whole point about this talk is that I want you to realize that these numbers they fill up the whole real line, in the sense that the real line is for the most part filled up by these numbers, but yet we do not know enough examples of these numbers. Okay, so and what do I mean by enough examples is something that I'll illustrate. So for example, you know, so you've all seen, you must have probably come across this, the statement that, for example, E and pi, they are transcendental. And the fact is that if you take an algebraic number, see the algebraic numbers, of course, you know, I could have, instead of taking, saying that it satisfies a polynomial with rational coefficients, I could have as well said it satisfies a polynomial with integer coefficients, because you can always clear denominators. Okay, and so if you look at, so basically, you know, you are trying to look at solutions of polynomials over the integers. Okay, and these are the algebraic numbers, right? They could very well be, they could be non-real, okay, and they could be complex. For example, I, which is the square root of -1, is one such. Okay, but the point is that these numbers, as a subset of, if you consider them as a subset of the real line, namely those among these which are real, they are only countable in number. Okay, so if you look at the real line and look at the rationals, that's, of course, the rationals are countable. Okay, and we know that the real numbers are uncountable. So it's often seen in a first course in analysis that therefore the irrational numbers are uncountable. Okay, and though the rational numbers also do fill up the whole line, in the sense that topologically, if you take the closure of the rational numbers, you get the real numbers. Okay, but a measure of size is by means of countability. Okay, tells you that the irrational numbers are far more than the rational numbers. Okay, and in the same way, if you look at so this is the real number sitting inside the complex numbers, and then there is this object which is Q bar. These are the this is the algebraic closure of Q. Okay, namely these are all those complex numbers which are algebraic over Q, and this is of course the algebraic closure and this is a field extension, and this sits inside the complex numbers. Now, the fact is that this set, if you intersect it with R, you're going to get all the algebraic numbers which are real, okay? And what I'm interested is in the complement of that, okay? So this set is also countable, okay? So the algebraic numbers can be counted, and that's the reason is because you can count them. So for example, you can take polynomials of a given degree with integer coefficients, okay? And that's and you can take then polynomials of different degrees, okay? And in this way, you can use the fact that a countable collection of countable sets is again countable, and in this way you can literally show that all the rational and all the algebraic numbers are also countable, okay? Therefore, given the fact that the real numbers are uncountable, the complement of the algebraic numbers in the set of real numbers, namely the transcendental numbers which are real, that is an uncountable set, okay? And it's again therefore and in that sense, these transcendental numbers, they also fill up the whole real line. And the point is that we know very few of them, okay? So there is E and pi which are transcendental, okay? And I'll try to indicate some proofs of transcendentality of E and pi, okay? Then the other example is that of is that given by so here is a problem which is often called as Hilbert's seventh problem, and so the problem is that if you take an algebraic number and raise it to the power of another algebraic number which is not rational, okay, then the result is a transcendental number, okay? So the statement is A comma B algebraic, and of course B irrational. This implies that A to the power of B is transcendental. So of course you have to put the restrictions on, of course B should not be 0 or 1, and you have to put such restrictions, obvious restrictions. But this is an answer to, this is a question of Hilbert. It's the Hilbert's problem, and it was proved by Gelfand Schneider, okay? And so if you, since we know a lot of algebraic numbers, and since we know a lot of, among the algebraic numbers there are of course a lot of irrational algebraic numbers, then you can use this to get lots of transcendental numbers, okay? And so see, the advantage of this is, for example, you can say things like, you know, root 2 to the power of root 2, or 2 to the power of root 2, and then e power pi, which is actually e power I pi to the minus I, and that is well, I power, I think, is that right? Yes. So this I to the minus I. So this is also by this theorem transcendental, okay? And you also have I think also e power pi by 2 also in the same way, okay? All these chaps can be deduced to be transcendental using this result, okay? But it's rather funny that if you take so these are all transcendental. But of course, you know, if you take things like, if you on the other hand take pi to the e, we do not know whether it is transcendental or. Oh, sorry, this should be minus 1. Sorry. Yeah. Okay. Yeah. Thank you. So So that's right. Thank you. So if you take several other numbers, for example, you take pi to the e, you can't see, it's not known whether it's transcendental or not. Okay, and then if you take things like, so for example, zeta 3, which is the value of the Riemann zeta function at n equal to 3, which is actually sigma 1 by n cube, n equal to 1 to infinity. This is known to be irrational, but one doesn't know whether it is transcendental. Okay, and then of course Euler's constant, okay, which is the difference of the harmonic series and the log as n tends to infinity. Okay, that is also known to be irrational, but one does not know whether it is transcendental. So there are lots of these fellows about which you do not know anything about transcendentality. But the point is that if you want to get, if you think, so you know, if you think of transcendental numbers as stars and the real numbers as the sky, well, then the transcendental numbers they fill up the real numbers in that sense, but you don't know lots of examples of transcendental numbers. One does not even know whether certain irrational numbers are transcendental. Okay, and I do not know. I'm not an expert in this. But if you take things like pi plus e and things like this is also probably the status of this numbers like this is also not clearly known. Okay. Is not even known whether it is even rational or not. Yeah, so you see, whether something is rational or not, and if it is irrational, whether it is transcendental or not is a non-trivial question. Somehow, as a geometer, I can see that rationality is non-trivial, because in geometry we study varieties, or more generally we study zeros of polynomial equations, and it's very difficult to say whether you can find zeros with values in a certain ring or a field. It's very, very difficult to say whether there are valued points. And so one can see from the sense of geometry, from the viewpoint of geometry, one can see that even rationality itself, namely that there is a rational number which satisfies this condition, the conditions that you are implying, the definitions of the number that you know of, to even to decide that is not trivial. Okay, so but if you look at this statement, I still only get a countable collection of transcendental numbers, because after all I am tracing an algebraic number to another algebraic number, all right, and the algebraic numbers are just anyway countable. Okay, so the set of all these numbers gives you only a countable collection of transcendental numbers, but the transcendental numbers by themselves are uncountable. Okay, so the question is there is to get a huge collection of, say, uncountable collection of transcendental numbers, one can go back to the work of Joseph Liouville. Okay, so there are the so-called Liouville numbers. Here, a real number x that satisfies the following condition. Is called Liouville. So the condition is that, you see, for every integer n greater than or equal to 1, okay, there exists p and q integers with q greater than 1, such that if you try to approximate x with the rational number p by q, okay, then this is a strict approximation, and the error is lesser than 1 by q to the n. Okay, so this is the definition of what a Liouville number is. So as n becomes larger, of course the p and q that you get will depend on the n, but there has to be for each n as a particular p and a q with this property. Okay, so which means that as n becomes larger, of course this quantity is going to become very, very small. So that means that you can approximate a Liouville number very closely by rational numbers. Okay? P? There exists P and Q. There exists P and Q integers, Q greater than 1, such that this inequality, such that, okay, so maybe I should write such that P and Q are integers. Oh, this P, okay, maybe I'll write it. This is better. Yeah, so these numbers are called as Liouville numbers, and the fact is that that these Liouville numbers they give us an they are an uncountable collection, and they are actually transcendental numbers. So this gives you an uncountable collection of transcendental numbers. Okay, and therefore at least one is happy that one has. But again, so the question is, what about existence? So at the outset, let me tell you, there are these Liouville numbers. There are uncountably many of them. They are all transcendental. Okay, and but they still fall short of our expectations, because you see, the title of the talk was that you have a sky filled with stars and you are not able to see many of them. So one can be happy that one has an uncountable collection of transcendental numbers, but from a somehow measure theoretic point of view, all these Liouville numbers, they still are set of measure 0. Okay, so in that sense, they are still we have still not able to find a collection of uncountable collection of transcendental numbers which is let's say positive measure. So even if you take an epsilon interval, an interval of length epsilon, it still has positive measure. Okay, so the only nice thing about these numbers is that there are uncountably many of them. So at least you have an uncountable family of transcendental numbers, but still it is not much from the measure theoretic viewpoint. So, but anyway, so what are the examples of such numbers? So the examples are, what you do is you take any integer b greater than or equal to 2, and then you take a sequence a1, a2, etc., which are the digits in the base b decimal representation, base b representation of the number, okay, base b expansion, and these are all therefore to be digits from 0 to b minus 1. Okay, and what you do is you take the number x to be sigma k equal to 1 to infinity ak by b to the factorial k. Okay, so this is, so what you are doing is you are just taking 0 dot a1, a2, and then now the next position is this factorial 1, this factorial 2, factorial 3 is 6, therefore 1, 2, 3, 4, 5, 6. Okay, the next position is factorial 4, which is 24. So I'll have zeros, I'll have 17 zeros in between, and I'll have a3, and so on. And this is a representation to the base b. So you look at this, look at these numbers. The fact is that the entries in the expansion, the base b expansion, they are sparse in the sense that there are a lot of zeros, and then you have the number of zeros keeps on increasing. Okay, in fact here it goes by factorial. I think even if you take you put one number and then you put 1 0, and then you put one more number and then you put 2 zeros, and then you put one more number and then you put 3 zeros, and you do this, that also will give you a number which is transcendental. Okay, so the fact is that there are a huge number of zeros which separate the digits, and this, the way this is written, this expansion is certainly not it's not a rational number, because it's a non-terminating, non-repeating kind of expansion. And the fact is that this is, so it's an exercise to verify that these numbers satisfy the Liouville condition. Okay, so these are so it's an exercise to show that these are Liouville numbers. I mean, these are also Liouville numbers. So exercise is the examples above are Liouville numbers, and that's an exercise. And so let me look at some of the let me write down certain things. So what you can okay, so this is what you can, so you verify the following thing. You verify that you put Pn to be b power n factorial, okay, and you put you put Qn to be b to the n factorial, and you put Pn to be Qn times the series truncated at n ak by b power k factorial. So you take these values for Pn and Qn, and you can check that you have this inequality where x is of course this number, and that is 1 by Qn to the power of n. Okay, so you can verify this. It's a simple inequality, and this will tell you that these numbers are indeed Liouville numbers. Okay, and as far as this gives you the proof that Liouville numbers do exist. Then the other thing is that all these Liouville numbers, they are all only rational. I mean, they are all irrational numbers. Okay, so in fact, my claim is that as was proved by Liouville, these are all transcendental. Okay, and so here is a proof of the fact that the Liouville numbers are irrational. And well, the key to that is the following calculation. You see, if you calculate, take a rational number c by d, okay, and try to calculate the error in pardon? No. To begin with, irrational. Pardon? Is something wrong? No, I'm not proving they are transcendental. So first I am trying to show that they are actually irrational, okay, and then the next step is to show that they are transcendental. Of course, I could directly prove they are transcendental. Yeah. So so what you can do is, see, if you take any number of the form c by d, a rational number of the form c by d, and try to calculate the modulus of difference c by d minus p by q, what you will get is that this is at least greater than or equal to 1 by q to the n. Okay, if you choose n greater than 1 plus log n is greater than 1 plus log to the base 2 of d. Okay, so you can show this. Okay, and so what this tells you, see, the fact that this error is at least 1 by q to the n. Okay, if you choose n sufficiently large, I mean, if you fix a c and a d, okay, and of course d is not 0, and you try to approximate c by d by a rational number, but mind you, I am not trying to approximate. I can of course exactly approximate c by d with c by d itself. That's not what I am supposed to do. I am supposed to approximate it not exactly, okay, because that's part of the definition of the real number. Of course, if this is 0, then it means that your real number is a rational number, okay, but it cannot happen. In fact, that's what this calculation tells you. See, if you take a c by d which is not equal to, and you take a p by q which is not equal to c by d, namely this, if this modulus is greater than 0, okay, then this always exceeds 1 by q to the n, provided you take n to be greater than 1 plus log d to the base 2. And what this tells you is that therefore you cannot approximate, any rational number cannot satisfy the Liouville condition. In other words, it tells you that every Liouville number is irrational. Okay, so it is just based on this inequality, right? Then the other thing is transcendentality of this of these numbers is something that. So let me make a remark about the transcendentality of these numbers, and that again is so the idea is similar to this, in the sense that what we have proved, what I've written down there is that if you take a rational number of the form c by d and you are trying to approximate it by another rational number, okay, then this approximation is not going to be good if you choose n large enough, all right. I mean, it's not good in the sense it's not good enough to make it Liouville, okay. So if you try to if you translate that idea to algebraic numbers, so what the next important lemma is that it's called Liouville's lemma on Diophantine approximation. So it says that if you take a algebraic number which is not rational, then of course it satisfies a polynomial, and then the fact is that you cannot the accuracy in trying to approximate that by a rational number, okay, in this Liouvillean sense, you cannot get an approximation better than n, which is the degree of the polynomial that it satisfies, okay. At least that much error you will always get, okay. So that is a statement which will tell you that none of the Liouville numbers is algebraic, okay. So here is this lemma. So this lemma says that if alpha irrational and algebraic, alpha satisfying a polynomial of degree n, which it has to do because it's algebraic, okay. Then there exists a positive constant such that if you try to approximate alpha by a rational number p by q, okay, no matter what your p and q are, of course q is of course not 0, then this error is always greater than a by q to the n, okay. So in other words, if alpha is algebraic and satisfies a polynomial of degree n, okay, trying to approximate it by a rational number, you will get at least this much of error, okay. And see, this will tell you that I mean, you can use this to deduce that none of the Liouville numbers are is algebraic, because we all know that they are already irrational. So if you assume they are algebraic and irrational, okay, then the Liouville numbers have to satisfy this lemma, and you can see that this is the opposite inequality of that up to a constant. You can fiddle around and try to get a contradiction to this, okay, by choosing p and q carefully, okay. So this is the above lemma can be used to show that Liouville numbers are transcendental. And of course, as I told you, there is also this fact that if you take the measure of the set of all Liouville numbers at 0, okay, that is something that I'm not going to prove here. You can look it up. But in any case, at least the advantage with Liouville numbers is that you have an uncountable collection of, transcendental numbers. Now, what I want to do is that I want to explain give some idea about proofs of transcendentality. So there are, you see, if you take E and pi, there are proofs which basically involve a simple analysis. Okay, basically they involve playing around with derivatives and integrals of a function of a real variable, and then using all your standard stuff from a first year calculus course, namely using the mean value theorem and things like that. So that is one. These are the kind of proofs that one can very easily understand, but though they will involve a little bit of computation. Okay, so to give you a flavor of such proofs, let me explain the proof of one such proof, which is that of transcendentality of E. Okay, so here again, I'll only write the key steps so that you can check for yourself. And of course, anyway, all this material is very available in several books which you can refer to. So in all these cases, the idea is both the old proofs of E being transcendental and pi being transcendental is by starting assuming that they are in fact not transcendental, namely that they are algebraic, and then trying to get a contradiction. And the proofs somehow go like in the following way. You somehow obtain, or I should say, whoever proved it was clever enough to obtain by sequence of steps an identity, and prove cleverly that one side of the identity is an integer and the other side of the identity is not an integer. Okay, and that gives a contradiction, and that's how these proofs go. So here is an example. So proof of E being transcendental. So for this, what you do is by contradiction, you assume that it is not transcendental, namely it is algebraic. So you have it satisfies a polynomial equation with integer coefficients. So I have these Ci's which are integers. So you assume that such a relation holds. This is the same as saying that E satisfies the polynomial C0 plus C1x plus C2x squared plus etc. Cnx to the n, which is a polynomial with integer coefficients. Okay, so which would mean that E is algebraic. You start with this. Then what you do is you do the following thing. You make a kind of transform. So what you do is you define fk of x to be x power k times x minus 1 and so on up to x minus n whole to the k plus 1. You define this function. It's a polynomial of degree 2k plus 1, and yes, and what you do is you multiply both sides by so you put this multiply so this equation, if you call it a star, by integral from a to b fk e power minus x dx. Okay, and of course and let a tend to 0, b tend to infinity. Okay, you can check that this is this improper integral will exist, and it will define a finite quantity. You multiply both sides, and then what will happen is that you will get an equation like this with this term in each of those multiplied with each of those coefficients. And then what you can do is that then comes the important step. Once you multiply this with that, you will again get that product equal to 0. Okay. Then the left hand side, this integral, you see this integral which is going to be integral from 0 to infinity, that integral can be split at various integer values. Okay. So for Ci you split it from at I. Okay, you go from 0 to I, and the left side becomes you can split the sum the left side as a sum of two terms. Okay, one set of terms coming from the integrals from some finite integer to infinity, the other set of terms containing the other part of the integral, namely from 0 to that term. Okay, and for Ci you split the integral as 0 to I and then I to infinity, and you write down two terms. Okay, so what you will get is you will get something like this. You will get, so let me write it here. So what you will get is, so you will get P plus Q is 0, where P is the one that contains the latter part of the integral, namely C naught 0 to infinity fk e power minus x dx plus C1 1 to infinity C1 e 1 to infinity fk e to the minus x dx, and so on, plus the last term will be Cn e to the n integral from n to infinity fk e to the minus x dx. And of course Q is going to be, Q is going to be the other term. Okay, and then it's a calculation, it's just a calculation which involves very simple integration. Okay, basic integration which will tell you that, you know, if K is chosen properly, so you see this K has been, this K is a parameter which is something that we leave, we leave it in our control to choose, so that it satisfies whatever requirements we want. So if you choose pick K properly, what will happen is that P by K factorial is a non-zero integer, and it also will turn out that Q by K factorial will be a fraction. For large K. Okay, and once you can establish both of these things. Are quite easy, and the proof of this involves using this following limit K tends to infinity lambda power K by factorial K is 0. You use this, that being essentially the kth term of the expansion of e power lambda, which is of course a convergent series. So the kth term has to go to 0. So you use this to prove this bound, and you know that the other one is a non-zero integer, and then you get a contradiction to this. Okay, if you take Q to the other side and take mod and divide by K factorial, you get a contradiction. So this is an idea of how you prove that E is transcendental. Now there's a much more general theorem which, since I know that, I've been told that many of you are also master's students, so I think there's a much better theorem that can be used, and my favorite book for the purpose is of course Lang's algebra, which is my favorite book for algebra, and I know several people probably will resent, but there is a very nice appendix to this book which gives a proof of a statement which will prove both the Hermite-Lindemann theorem and the Diophantine theorem in one stroke. And so let me at least state that result, and that result as a corollary will give you both the transcendentality of E and pi in one stroke. So basically it has got to do with trying to get bounds for holomorphic functions, bunches of holomorphic functions which are linearly independent and taking values in a number field. Okay, so let me just state the theorem so that you can. So our situation is like this: that is Q and that is K. This is a finite extension. So this is, in other words, K is a number field. It's a finite, of course, algebraic extension of Q. And what you're doing is that you have the complex plane, and you have a particular complex number, or you have a bunch of complex numbers, n points on the complex plane, and you have a bunch of functions f1, etc. up to fn. These functions are see, they are by definition meromorphic of order rho, and what this means is that they can be represented as quotients of entire functions of order rho, and a function being order rho is to state it in a simple way, if you take the model of the function, that is that should be of this form. It should be bounded by c to the power of r rho, okay, where r to the rho, where mod z is less than or equal to r and r sufficiently large. Okay, so and c is, of course, I should say, is like, you must think of c as e, so it should be a positive constant greater than 1. So this is how you would define in a reasonably simple way what an entire function of order rho is, and then you take quotients of such functions, and these functions are of that type. Okay, and the point is that if you evaluate these functions at these points, you should land in the number field. So these meromorphic functions, they should take values in the number field. Okay, then it's and of course you also assume that f1 through fn are algebraically independent. You assume this. Yes, so then you, of course, these are all functions, wherever they are holomorphic, you can therefore differentiate them, and of course you assume that they are holomorphic at these points, so that you can evaluate them. Okay, so they are holomorphic at these points, and you assume also that differentiation by z, where z is the variable, the complex variable, this takes the field, the field generated by this over this number field back into itself. So k f1 etc. fn goes back into k f1 etc. up to fn. You assume this, all right? Then comes the following. So it's basically a bound. M cannot exceed 10 rho times the degree of the extension of k over q. So this is the. This is essentially the theorem, and you see, from this theorem you can get whatever you want. Say, for example, if you try to, so basically what it says is, if you evaluate these functions at several points, okay, then there is a restriction on these functions taking so many field values at so many points. I mean, this m cannot be this m cannot be unbounded, and the bound is in terms of the order of the function and the degree of the extension. And now what you do is, for example, if you apply it to the pair of functions z and e power z, okay, you get the you'll get the statement that E is transcendental, okay, and in fact you will also get the statement that if alpha is algebraic, then E power alpha is transcendental, okay, and you can also apply it to get the following. So you apply to this or to so if I want to apply it, if I want to get the case A to the B, then I should take a log and exponentiate. So if I'm thinking about trying to show that if A is algebraic and B is algebraic irrational, then A to the B is transcendental. Okay, then I write this as e power B log A. Okay, and therefore I apply it to e power I apply to Z and e power Z log A. Okay, and see, if you apply it to these functions, then you can see that you will get transcendence of E, you will get transcendence of pi, and you will get this general statement also that if A is algebraic and B is algebraic irrational, then this exponent is transcendental. And of course, the fact is that A and B can even be complex, okay, and then the statement is that one of these values, because it will be multi-valued, then the statement is that one of these values will be transcendental. Okay, so maybe I'll stop here, and I have been very sketchy, but I would request you to go through this appendix in Lang's algebra book at the very end, where this is done very well. The proof is very accessible. Okay, only thing is that it involves lots of computing lots of bounds. Okay, but it can be broken down into several lemmas which are all completely within the reach of a master student. So I would urge you to go through that proof. Okay, so I'll stop here.
Questions? If there are no questions, let's thank the speaker for giving a very about real numbers and transcendence and E, pi, and nice proofs about these things. Let's thank him once again. Thank you very much. Thank you.